Okay, so you guys completed this how fast does the flu spread problem. And so hopefully you got something similar to what I did on number one. So it increases really rapidly at first, really, really fast. And then at some point it starts leveling off. Why do you think it does that? Don't look at what I said. Why do you think it does that? Yeah, once everybody's sick, there's not any more people to infect. So there's only 1,000 people in Calculopolis. And so that's why it starts leveling off, okay? And then this, I think you guys, I kind of saw some of the stuff you were doing yesterday, grows the fastest right around 11 or 12, and that's when there was the steepest slope. And then I did ask you to find the maximum of f prime of t. If you didn't do that, the max occurs at 11.454, and I did want you to add that to the end of your table. I think next time I'm going to put it in the middle so you can see. I wanted you to see really what happens at the maximum of the first derivative. I wanted you to see what happens during the second derivative at that point. So at the maximum of the first derivative, the second derivative is 0. Is that surprising to you, or does that make sense? I hope it does, because the second derivative acts like the first derivative does to the first derivative. So like the first derivative would be 0 when the original function has a maximum in. So the second derivative will be 0 when the first derivative has a maximum in. And then I wanted you to see the relationship between when the first derivative was increasing and what was happening with the second derivative. It works just like the first derivative to the original function. So if the first derivative is increasing, the second derivative should be positive. And when the first derivative is decreasing, the second derivative should be negative. All right, so I didn't want you to see that very last line. So that last question says, how can you use how can you get your answer to question 4 just by looking at the graph? So do you guys remember from the graph from last year?
Concave.
Yes. So when the rate of change is increasing, what should the graph be? Concave up. And that's what happens from here to about wherever that max was of the first derivative. And then whenever the rate of change is decreasing, then the function should be concave down. All right, so jot that down if you didn't. So this is where a lot of the stuff we learned last year actually really helps us in calculus. And hopefully that's something you remember. I felt like we talked about it all year. All right, so let's talk about today's lesson. So we're going to be analyzing the behavior of a function using the second derivative. And so I think you're going to remember this from last year, but the graph of f is concave up when f prime is increasing, just like we just said. All right, and so if we drew little baby tangent lines where the graph was concave up, it's kind of hard to do it here. Oh, you can definitely see it on the bottom. The graph is going to always lie above all the tangent lines when the graph is concave up. It's kind of hard to see it on that graph. It's a little blurry. All right, and then the graph is concave down, then f prime is going to be decreasing. Alright, and then if we drew little tangent lines, they're all going to be above, so the graph lies below all of the tangent lines when the function is concave down. That's going to come into play later. We'll talk about it again when we talk about over and under estimates, so something to keep in the back of your mind. All right, and so to do a test for concavity, you're going to use the second derivative. So when that second derivative is positive, the graph is concave up. And when that second derivative is negative, the graph is concave down. Do you all remember what a point of inflection is? We talked about it last year, not a ton.
Where it changes from
Very
concave
good.
down or concave up.
Awesome. So when it changes from concave up to concave down, or vice versa. So it's a point at which the concavity of the function changes. All right. Just some things to keep in mind about the point of inflection. The function must be continuous. On the open interval containing the point of inflection, the tangent line must exist at the point of inflection. However, we can have a slanted horizontal or vertical tangent line. And if we have a point of inflection at C, then either f double prime C, so the second derivative at C is 0, or that second derivative at C is undefined. It would be undefined in the case of a vertical tangent line. And you can kind of see that on the cube root graph. There's a vertical tangent line at 0 on the parent function, and it's also a point of inflection, changes from concave up to concave down. And then for the cubic, it is a horizontal tangent line. Okay, here we go. So this is another just example of the tangent line either being above or below. So we're going to go on to the second derivative test. So do you guys remember the first derivative test? I hope so. Yeah. Okay, so the first derivative test is a test for a relative max or relative min. And when will you have a relative max? When the first derivative does what?
Goes from positive to negative.
Yes, changes from positive to negative. That's the first derivative test. And then you'll have a relative min if the first derivative changes from negative to positive. And that point that you're testing is a point of inflection. A point of inflection is always a potential relative max or relative min. So let's say that you do have, I meant to say critical number. Sorry. So the critical number is a potential relative max or relative min. So on the second derivative test, we still have a critical number. And we're trying to figure out if it's a relative max or relative min. And let's say it's a situation where we can't do the first derivative test and we need to do the second derivative test. So you have a critical number, and then you plug in that critical number to the second derivative, and you get something greater than 0. So think about it for a second. If the second derivative is greater than 0, is it concave up or concave down? Concave up. What is that going to be for concave up? Relative minimum. Very good. So let's say you still have a critical number, you plug it into the second derivative, and you get something less than 0. That means we're concave down, so that's going to be a relative maximum. Right. And then if you plug it in and you get 0, then it fails the test. It's non-conclusive, so then you would have to do the first derivative test. It's a good chance it's not a relative max or min. It might be a point of inflection instead. Okay, so we are going to do a whole lot of things on this example. When you guys go to do your assignment, you don't do all these things except for one problem. So it'll just ask for one of the things. So don't think that every problem is this whole thing. And so what we're going to do is we're going to find all the things. So we're gonna find where the graph is increasing or decreasing. And just a reminder, increasing and decreasing are closed intervals. because you can't be increasing or decreasing at a point. You're increasing or decreasing between points, so that's why we make those closed intervals. All right, we are going to find, which we've already done that. It was on your quiz yesterday. You guys did great. We're going to find relative extrema. We've already done that. It was on your quiz yesterday. You did great. We're going to find the intervals where a graph is concave up or down. That is going to be open intervals. And I know it's hard to keep straight. The difference is a point can be considered concave up or concave down. A point on the graph, so if we have a graph like this, and someone asks you, is the graph concave up or down at that point? You can answer that question, right? So you can't say, is the graph increasing or decreasing at that point, because it's not moving, it's just there. All right, so that's the difference. All right, we're gonna find points of inflection, that's new. And then we're gonna do a graph with all the right concavity, all the right increasing and decreasing points. It's gonna be glorious. All right, so before we can determine where a graph is increasing or decreasing, what do we need? Yeah, we need the derivative because we need the critical numbers. That's perfect. All right, so let's go ahead. That was good teamwork right there. We're gonna find the first derivative just by doing the power rule because it's a polynomial. All right, then we're gonna make sure we label that the derivative. All right, and then we're gonna go over to the side and we're gonna find our critical numbers. And I did say it wrong earlier, but the critical numbers are potential, relative max and relative minimums. There are also points where the function will change from increasing to decreasing or decreasing to increasing. So it's important that we find these. I'm going to factor out a common factor of negative 15x squared. You can do positive 15x squared if you want to. It just makes it a little easier to work with if we do the negative. All right, so we have 3 critical numbers. And then to find where the graph is increasing or decreasing, we're going to take those and we're going to put them on the number line. All right, and then we're going to test a point in each region. And what are we testing it in?
The derivative.
Yes, the derivative. So we're going to do f prime of negative 2. F prime of negative 0.5, F prime of 0.5, and F prime of 2. Okay, so I have 3 sets of factors I'm going to plug it in. First factor, negative 15x squared. Always negative, because everything that we put in and square it, we get positive, and then we multiply that by negative 15. So let's just go ahead and make that guy always negative, and we don't have to worry about it. All right, and then we can plug in our negative 2. Negative 0.5. And then 2. Alright, now I like to draw the little arrows that show increasing, decreasing. Now that, oh my goodness, I'm sorry. that does not answer the question. So I'm pretty sure, I feel like there was somebody yesterday, maybe you just forgot to go back and answer the question. But drawing that doesn't answer the question. You have to say the intervals of increasing and decreasing. So let's start with increasing. So what that will count for showing your work. It just won't count for answering the question. All right, so we start increasing at what x value? -1, and we're going to increase all the way to 1. All right, and then negative infinity to -1 is decreasing, and then 1 to infinity will also be decreasing. And then part B, we are going to identify the relative extrema. So the arrows also really help you see that, because we know if we're changing from decreasing to increasing, we get a relative minimum there. And that is when the x is -1. Now we will need to plug that into the original function. Writing it out. Plugging in -1 and 1 is pretty easy. You can do that in your head. But it looks like we're going to get 3 minus 5, or -2. I'm writing too big. We have a lot to fit. Okay. And then because the first derivative changes from positive to negative, I have a relative maximum at 1. And then 1 is super easy. You just add the coefficients of the original function. So -3 plus 5 is going to be 2. Okay. You guys wrote smaller than me. All right, so let's do the C part. And the C part is the new part for this year. So we're going to state the intervals where f is concave up and concave down. What do I need for that? Second derivative, good job. So that's going to be -60x squared plus 30. -60x cubed plus 30x. Okay, so we're going to do a similar thing to what we did right here. We're just doing it with the second derivative. And we don't call them critical numbers for the second derivative. That's just the first derivative. But they are potential points of inflection. All right, so let's take that second derivative, and we're going to set it equal to 0. Okay, so definitely 0 for the outside one. 2x squared minus 1 won't really factor, so we can just set it equal, I mean it would with a radical. We'll just set it equal to 0 and solve it. Take the square root of a fraction, you just do the square root of the numerator, which will be 1, and the square root of the denominator, which I'm just going to leave the square root of 2. Alright, so the square root of 2 is about 1.4-ish, just like 1.41 something, something, something. And so when we're trying to figure out, something bigger than that, something between that and 0, it's a little confusing. I'm going to start on the positive side this time, which I never do. And so can you think of something bigger than 1 over 1.4? An easy number? 2, we could do 2, we could do 1. Both of those are bigger. So anything bigger, positive-wise, the denominator would be smaller. All right, what about in between 0 and 1 over 1.4? Yeah, good. All right, and then we'll just do the negative versions of those numbers over here. Oops. There we go. Okay. Alright, so just try to remember, we just need positive negatives. Don't let this be too frustrating. But when I plug negative 1 in, is something wrong? Okay, when I plug negative 1 in and I multiply it by negative 30, that's definitely a positive. Alright, when I square it, multiply by 2, subtract 1 from it, that's going to be a positive. Okay, and then negative times a negative is a positive again. But this time, when we square negative 1/2, we get positive 1/4. And then we'll multiply that by 2. It gives you positive 1/2. And then subtract 1, and we get negative. Right? And then negative times positive 1/2 is going to be a negative. Right, and then the same exact thing that just happened with negative 2, when I put it here, it's going to happen again. So we square it, we get positive, multiply it by 2, all that stuff happens and we get another negative. So that would be positive. Right, and then when I put 1 in, I could just go back to the original if I wanted to and just add the coefficients. That's going to be a negative. So what was this question? This question was concave up or concave down? Yes. All right. So try to remember, and I know it's a lot, you have so much to remember, but concavity intervals are open intervals. And so we are concave up from infinity to negative 1, and then from 0 to 1 over the square root of 2. So anytime the second derivative is negative, we're concave down. That's going to be negative 1 to 0 and 1 over square root of 2. Oh, no. Sorry. I don't know where I'm getting negative 1. Maybe I should have just used my video from last year. Negative 1 over the square root of 2 are those endpoints.
Wait, should be negative infinity on concave up?
It should be, thank you. Okay, so the only points that are changing concavity should be the infinities, positive, negative, square, 1 over square root of 2, and 0. So I think I have it right now. Right, and then on D, we want to find the points of inflection. And just to save on time, and you guys can do this too, I don't really want to raise 1 over square root of 2 to the 5th. I just don't want to do it. So I'm just going to tell you, I did it in the calculator. So we will have points of inflection where the concavity changes. So earlier I plugged in negative 1 over the square root of 2, and I got negative 1.237. And I plugged positive 1 over the square root of 2, and I got the positive version of that number. Oh, I'm totally out of room. Alright, we're we're gonna have to find a way to squeeze a little graph on. Now, this graph doesn't have to be very big. We're only, like, the highest it goes is 2, and the lowest it goes is -2, and then it's not very wide, so you can maybe have some room to squeeze it on there. I'm gonna go with the back. You can graph it on the back of your other page if you want to.
And we skip her,
Hey.
is 0 not a point of inflection? It goes from negative to positive?
You're absolutely right. Thank you. What would the y be when we plug in 0?
0.
Yes, thank you. Okay, so let's graph our relative extrema. So -1, -2, +1, +2. Alright, our points of inflection, we have one at 0. We have one at, I didn't type that in. 1 divided by the square root of 2. Sorry, my calculator's super slow. Alright, 1 divided by the square root of 3 is 0.707. Alright, so at -0.707, and then negative about 1.2, we have a point of inflection. And then a point of inflection at the positive versions of that also. Alright, and then we want to start off decreasing, right? So when we did our little table right here, we decrease all the way to where x is -1. So we'll do that, we'll be decreasing. Now this is a polynomial function, so we will have smooth rounded turns. Oh, we are also concave up there. So according to our other number line, for the second derivative, we're concave up all the way until we get to that point of inflection. So we change over to increasing, but we're still concave up. Alright, we're going to increase all the way to the maximum here, but concavity is going to change twice. So between this point and this point, we're going to be concave down. Alright, and then we're going to be between this point and this point, we're going to be concave up. Right, and then the rest of the graph is concave down. We're increasing all the way to the max, but concave down. And then decreasing and concave down all the way. Okay. So we did a whole beautiful graph with, I only used the calculator, just one little point. Alright, any questions on it? That's all the things.
Oh, that's it?
I mean, that's all the things we've learned. We're gonna do a couple more examples. So on this one, we are given the first derivative. We're going to use the second derivative test to find the x-coordinates of any relative extrema. Okay, so we obviously need the second derivative. Ooh, we need something else too. So don't forget that on the second derivative test, you need a critical number. So is that critical number going to come from the first derivative or the second?
First.
First. Okay. Alright, so we want to know when this guy is equal to 0 or undefined. It will never be undefined. So what we need to do, we don't have to do any table, any number lines or anything. I'm just gonna take those critical numbers and I'm gonna plug them into the second derivative and see if we get a positive or a negative. So for -2, I'm gonna get -4 minus 2, which is a negative. So what does that mean we have at -2? Concave down and a relative
Max.
max. Okay, let's see if I can squeeze the other one. So we also are gonna check 4. That's gonna equal a positive. So x equals 4. So relative is the location of a relative min. It isn't the min. It's where the min lives.
For the relative max, wouldn't it be -6?
I just put negative, sorry. I didn't say what it is. I just said it equaled to negative. So that means that there is a relative max at x equals -2. I mean, we can make it -6, it's fine. And that one is gonna equal +6. But what I was just saying is this is the answer to the question. That's where there's a relative max.
Okay.
I just said it equals a negative. I was trying to save time. Alright, bless you. What about critical number on B? There's only
3.
one. Close. Did you say?
-3.
Yeah. For a second I thought I just didn't hear you. Alright, critical number is x equals -3. That's a potential relative max or relative min. So you guys use the second derivative test to decide what it is. Alright, well, there's nowhere to plug in the -3, so this second derivative is always positive. So what does that mean?
There's no fact.
Is concave up or concave down? It
Um,
only fails if you get 0. It's concave up, so what is there?
Relative max.
Yeah, relative min. That's a positive number. It only fails when you get something that's not positive or negative, like here. Okay, I know this is a forever lesson. We are gonna go back to the back of your paper you did yesterday. Okay, and this right here is how a way they like to ask this question. So we have this graph of f, and we want to determine all the intervals where the first derivative is positive and the second derivative is negative. So if the first derivative is positive, what does that mean for the graph? What is it doing there?
Increasing.
It's increasing, good. All right, what about the second derivative negative? What does that mean? Good job. Alright, so see if you guys can find a section between A and D where that happens. Increasing and concave down. Do y'all see one? B to C, good. And your justification would be because f of x is increasing and concave down. That's all I can think of. Bless you. Alright, and then number 2, for a twice differentiable function, that just means the second derivative exists. H of x. It is known that h prime of 3 is 0. What does that make 3?
Critical number.
Yes, good job. It's a critical number, and it's a potential relative max or relative min. And h double prime of 3 is negative 1.5. Concave down at 3. also means there is a relative max at 3. Okay, and we've answered the question. So which of the following statements could be false?